Okay, today is a bit late, but yeah, I guess it's better late than never, right? Okay, so let's say I'd like to go back on um binary search, um, which is a rather interesting topic, and uh, needs more practicing for me to actually understand what it's really about, right? So, let's see. I solved this question yesterday, which was on a 2D array, or in other words, a matrix, right? A matrix, and we're going to search for a particular value in the matrix. So one way we could do that is to iterate each row of the matrix and search if our target is within that row. Otherwise, we'll move to the next row. Since the row are also arranged in a way that the next value in the next row, the first value in the next row is superior to the last value in the previous row, right? So this is essentially how do I put it? Anyways, the rows are just sorted in ascending order, right? And it continues up until the end of the last row. Now, here is my solution for that. To solve this question, I'll just open this binary search. Yeah, so here is my solution, right? And this solution is quite different to what. So you must write a solution in O log m times n, right? Where m is the number of rows and n is the number of columns. But this time around, my solution is in. So we have. So we search within each row, right? Before we move. So we are searching within each row. So this is O, I think log m log. Sorry. Let's say we go through the rows, right? So current row. So we are searching within each row each time, right? And we're implementing the binary search. So it's binary search itself is in O log n, right? And we're also, you know, we're also iterating through each row, right? Which is O of n as well. So it's like O of n plus log n, right? Um, I don't know how to represent that. I probably didn't read much about it, but yeah. So um, I think one way to you know um implement this solution, right? This m times n, right, is to first of all transform this array into a 1D array, one dimensional array. Since currently it's a two-dimensional array, right, which means each row in the array in this matrix is actually an array. So we need to search, and our solution is should be in O log n times n, right? So currently our solution is in, I'll say, I don't know, since I'm iterating through each row, right? Since I'm iterating through each row, that takes O of n, right? Okay, my board is not on. Already that takes O of n time to go through each row, right, and look at each value to see if it actually matches our target. And then the binary search implemented on each row, right, takes O log n times, right? So I mean O log n time to compute. So I'm not sure why did I write it like that. It's supposed to be O log n, I think. Yeah. So O log n time to compute. So this is O of n, right? What the first for loop is O of n, and this one, so O of n and O log n, like this. So, but the question is asking us to implement the solution in O log m times n. M times n, m times n, m times n, blah blah blah. So I will just move this to this side, right? Let me take this image and show you how we can do that. So I'll remove this, I'll copy this image and delete everything from the screen, right? So let's see. Okay, so first of all, we need to treat the entire matrix as a one-dimensional array, which means our first item in the array is going to start here and our last item will be at this point here. Now, treating this as a one-dimensional array means we're going to, so the last item in this array, right, is going to be at position m times n minus 1, right? And the first item is simply going to be at position 0. Why is it m times n minus 1, right? Why is it like this? So first of all, we know m represents the number of rows we have, right? So if we count, right, we'll have 3 rows here. So 3 times how many, what's the length of this array within the matrix, or in other words, how many columns do we have? Because each array or each item in the array takes a position that represents the column of the matrix, right? So so this will be column 1, column 2, column 3, and then column 4, right? So times 4. But since we're not counting from 1, we'll simply count from 0, right? So instead of our row to be 3, this is going to be 2 times hold on, sorry, it's going to be 3. Since we are going to count, we are going to use the length of this row here. So m is going to be the number of rows, which is the actual size of the matrix, right? So this is going to be 3, and the size of the arrays within the matrix, right? So they are simply going to be the same, or in other words, the columns. So this is going to be equal to 4 minus 1, right? So this is 12 minus 1. This is going to be equal to 11. So when we start counting, right, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? But we'll start counting from 0 anyway, which is why we did that. So we said 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, right? 11 here. So with this, right, we can represent the left side, right, or the right pointer to begin the binary search on the entire array or the entire matrix itself. So let me erase that quickly. So I said our left and right pointer, right? Normally when we are performing binary search, we use 2 pointers, right? A left and a right pointer. So let me represent an array quickly. So 3, the array always has to be sorted. So we have our sorted array. We'll have a left and then a right pointer at this point. So these pointers appear at the end of the array, right? At each, end. So the left end and the right end. So for us to begin searching an item, we need to take the midpoint, and the midpoint is simply the value at which this left pointer appears plus the value at which the right pointer appears, right? In this case, it's going to be equal to 0 plus 3, right? Because the entire length of the array is 4, and the position of the right pointer is going to be at 3. So we do this calculation, divide by 2, we'll get 1.5, but we'll round this to the nearest 0, which is 1. So our midpoint, right, is at this position here, right? So this is our midpoint here. Now when we get the midpoint, what do? We check if the value at the midpoint is either equal or it's whether it's equal to the target. Let's say our target is maybe 7, right? Our target is 7, right? If the midpoint is superior to the target, right, which means it is larger, then we move our right pointer towards the left, right? Because we know the right pointer is actually going to point at a higher value since the array is sorted, right? So here's what we do: we move the right pointer towards the left. But when we find a value, when we find a value in the array that is actually inferior to our target, and we still have more items to look at, so what we do instead is we move the left pointer past the position where the right point, the current middle was, right? So we move it one past it, so it will appear at this position here. So at this position here, we have left equal to 3, so this is going to be 3 plus 3, right? Left and right can appear at the same position, divided by 2 again, right? This is going to be 6 divided by 2, which is 3, right? So in this case, the midpoint we have now will appear at this position, so this is going to be 3, and the value here is 7, which is simply equal to the 7 which is our target here. Now this is very useful because we did not spend our time iterating through the entire array, right? But instead what we did is to divide the array into half and search within the half to see if our value actually appears in that particular window or range, right? So the same thing will happen here, right? But this is just like a a smaller version of this question, right? This question is actually an array of arrays, or in other words, a matrix, right? This is simply this row here is an array, this is another array, this is another array. The entire matrix has a length of 3, right? The entire matrix has a length of 3, and each item in the matrix, or each array in the matrix, has a length of 4, right? Which represents n, and this represents m. So now what do we do next? So we will simply treat the entire array, right, the entire matrix, as a 1D array. In other words, as a simple array like this, right, with numbers sorted in ascending order. So here's what we need to do. We first of all need to take our left and right pointer, right? We know our left and right pointer always point to the end and the beginning of the array. Since we are treating this as a single or one-dimensional array, this will the right pointer, the left pointer will be at this position here, and then the right pointer will be at the last item in the array. And we know, since each item here, right, each item in the array or in the matrix represents a row. So for us to access this position here, right, this position at this point, we simply need to get the number of rows plus the number of columns divided by 2, right? So simply do this. So we take we so for us to get this position here, we need to take the number of rows plus the number of columns, not divided by 2. There's no division at this point. We are just trying to access the last item in the matrix, right? So here's what we need to do. We'll say right is simply going to be equal to m, which represents the number of rows, right? We have 1, 2, 3, right? So the number of rows here, right? We have 3 rows. This is going to be equal to 3 plus the number of columns. So we have 1, 2, 3, 4 plus n, which is the number of columns. So this is going to be 3 plus 4, right? 3 plus 4, which is equal to 7, right? This is going to be equal to r. So this is the value of r here. This is going to be equal to 7. Now 7, when we count the entire array, right? So let's say, hold on, what am I doing? So we are treating the entire array as a 2D array, right? The number of rows, not plus, it's multiplied. We are multiplying, right? Because when we try to traverse from this point all the way to this point, this is a multiplication operation, so we don't do addition. Sorry, that was my mistake. So instead of doing plus, we multiply to get the last item here. We multiply the number of columns by the number of rows, and since this is going to be 12, right, this is going to be equal to 12, but we don't have any item at the 12th position, right? We don't have any item at the 12th position. Instead, we have items up to the 11th position. So what we do is, after this operation, we simply subtract 1 from our results, right? So this is simply going to be 11. So we can then get the last item in this array. Now, what's the purpose of this, or what's the reason why we need to do things this way? Well, by getting the first item, or the left pointer at the beginning and the right pointer at the end of the matrix itself, we will narrow down how many times we need to travel across each row to search for our target, right? So instead, what we'll do here is, after getting this left and right pointer, right, this will act as indexes, right? So the midpoint we'll get here, we'll simply do this. So when we get the left and right pointer, so this is my left will be, my right will be 11, my left will be 0, right? When we add this together, what we normally do in binary search is we divide to the nearest 0, right? This will be equal to 11 divided by 2, 5.5, rounded to the nearest 0. This will be at position 5 here. So position 5 in this matrix does not actually exist, but what we need to do is, we need to position 5 actually exists, right? So when we start counting 1, 2, 3, when we start counting 0, 1, 2, 3, 4, 5, right, this will be at position 5. But what happens is, since we are trying to look inside this row, right, we need to convert this value here, this 5 here, to a much comprehensive we need to convert this value to represent the row we are in, right? 5 is all right. 5, the item that appears at position 5 is 11, but where is 11 in terms of rows, right? I mean, in terms of columns, this will be equal to 5. That is all right. But on what row, or which row does 11 appear, right? For us to get that value, we simply need to divide the value, the column by the amount of columns we have on that row, right? The current column we have right now is 5. So when we divide it by the amount of column on this row, which is simply equal to 4, then we'll round this value again back to the nearest 0 value, which is simply going to be equal to 1. And then we will know the row we are looking at currently will be at this position here, which is 1. The first row is at index 0, the second row will be at index 1. So this is how we will get the rows and the columns, right, for us to perform the binary search within that particular range. So when we get this row, now we can then go ahead and look for the mid value within this row, right? And to get the mid value, we simply need to take the midpoint, which is 5, right? We'll divide it by the number of columns here. So by the number of columns, right? Since we can't do direct division, because 5 does not technically appear in this row, right? When we start treating each row as its separate array, right, or as a separate entity, the count here is going to start from 0, 1, 2, and 3. But we have a value. Our midpoint currently, right, is 5, and this 5 represents the entire matrix, right? The column in the entire matrix, or let's say this 5 is just simply a point where the column and the row meets, right? So if you look at this is how many columns do we have. This is going to be 4 columns, but when we come to the second row and we continue counting the columns, we'll have column 5. We'll have column 5, column 6, but we start counting from 0, so this will simply be equal to 5 here. But we need to get the value at the midpoint here, right? We need to get that particular midpoint within the current row that we are in. So for us to do that, we'll go again and take that midpoint, divide it, find the modulus value, right? No matter how high the current midpoint or the current column we found, no matter how high that value is, right, the value of the current column we found is, let's say we have 5. When we divide by the length, or when we operate with a modulus operator with the length of the current row, right, we'll get a value, right? This will simply be equal to 1, right? So 1 column 1, in terms of columns, we have column 1. In terms of row, right, this calculation returned 1, and in terms of column, this is going to be equal to 1. So when we look at this, right, in the first column, right, when we look at this, counting from 0 in terms of rows, the row out position 1 is this row here. Let me erase all of this. The row at position 1 is this row here. So L is here. This is 0, 1, right? This is 1. And what value do we have at that particular position? We are going to look at 1, right? So 1 in this row will represent 11, which is where this 5 is, right? Since we can't use the 5 directly, we need to perform this extra calculation, and we'll get this value at this point here. Now we'll then compare, is this value superior to our target? And I did not know what the target was for this case, so let me just go ahead and look. The target here is 3, right? So if the target is 3, what do? We increase our right pointer, right? We'll push our right pointer forward. We'll push our right pointer forward, right? Sorry, our midpoint is here, right? The mid value will be here, which is 11, and our target is 3. So 3 is less than 11. Yes, so we move our right pointer, right? Our right pointer was supposed to be here. Let me represent it with a green color. So our right pointer was supposed to be here. Since the value we got now is actually since the value we got now is less, I mean it's superior to our target, and we know the right pointer is at a higher position, what we do instead is to move the right pointer, past the last occurrence of the mid value, right, or the last point where we calculated the mid value. So our right pointer will be here, and then we'll perform the calculation again to see whether we'll get the midpoint somewhere within this range, right, somewhere within this range here, right. We'll calculate it, and then when we find a value that is either going to be equal to 3 or less than 3 or superior to 3, we'll do we'll move either the left pointer or the right pointer at that particular point. So that is how we can optimize the solution that I provided yesterday. And with that, here we can implement the OM times O log M times N, right? So I'm not going to do that today because I really started late, which is bad. You know what? I would do. Okay, let me just do it since I've already explained it, right? Let me just implement it instead. So I will come here, right? I'll come here and create another folder. I'll call this let me copy the name of this folder here, refactor rename. I'll copy the name of this folder, this file, sorry, then create something else and call it optimized. So I'll say here, I'll put optimized like this, right? So that's the optimized version. So we know, let me just copy this, right, so that we can use it as our reference and use it to optimize our solution. So here's what we need to do. We need to treat our array as a single 2D array, as a one-dimensional array instead of two-dimensional array, right? Instead of a two-dimensional array. So let me just remove this. So here's how we are going to do it. The left pointer, right? So I'll say left, sorry. The left and right pointer. The left is going to be equal to, sorry, let me just put the two of them together. We'll have the left and right pointers here, right? So the left pointer is going to be equal to 0. The right pointer is going to be equal to the length of the matrix, right? So let me calculate that here. I will represent this by n. This is going to be the length of you know what, this is what I'm supposed to do. I'll just represent this by m, right? The length of the matrix, so the matrix, and n is simply going to be equal to the length of each row, right, or the amount of columns in the matrix. And we know every array in the matrix will have the same length, right? So we simply need to do length of the matrix I, right? We just take one of them and calculate the length. So here we need to say, okay, so now that we have the left, and we need to say right is simply going to be equal to the m times n minus 1, right? M times n minus 1. I'll just do it this way. I don't like how spaced it is, so let me just adjust this a bit. So m times n minus, please. I don't know what just happened. My network got disconnected. Everything is just unstable. Oh god. Christ. So let's do this. So while we have the left pointer can be less or equal to the right pointer, right? Which is, you know, the normal conversion in a binary search, right? Left is less or equal to the right. So, you know, we do that again. And here's what we need to do. First of all, we need to find the midpoint in the midpoint. So I'll just say mid is going to be equal to it's going to be equal to, hold on, the left plus the right. So this is going to be left plus right, left plus right, left plus right. Now we need to divide by 2, but we also need to round it up to the nearest 0, right? Left left plus right divided by 2, and that's our midpoint. Then what we need to do is to find the value at this midpoint here, right? So which means we need to get the row, right? So I'll say mid value, right? I'll just call this mid value, right? The value at the midpoint. So mid value is simply going to be equal to the matrix, right? Matrix. So let's get the column, I mean the row first of all. So the row is going to be equal to the mid value, right, divided by you know, divided by the length of the current row. So this is going to be divided by n, since we are representing the rows with n, right? And then how do we access the value in the column? So we will simply do mid, right? Mid, you know, the modulo operator n, right? Now, so we just say if mid value, right, is superior to the target, right? To the target, what do? We just simply reduce the left by 1, the right by 1. We shift the right towards the left, so we do is equal to whatever the midpoint is, the mid here, the midpoint is, we'll do whatever the midpoint is, we'll do -1, right? And else if the mid value is less than the target, right? When it's less, then we want to push the left pointer forward. So this is going to be equal to mid plus 1, right? And then we can just say we can just say else, right? If we've tested all these cases, then what's the question saying? We should return true, right? We should return true or false. So we'll just return, so meaning we found it here, so we can return true. Otherwise, when the loop is done running and we didn't return any true, we just return false, like this. So here is how we can search, you know, within the matrix. I'll just run a solution here. I mean, let's take this largest. This is not what I wanted to solve. Let's go. So we can do this. I'll just take the current value. Where do we have it? So yeah, okay, so this is our matrix, and the target is 3, right? So if this returns true, then it means we've passed that case. So I'll just say so I'll say solution, right, is going to be equal to, I think, solution here. We create an instance of the solution class, and then we call, you know, print, print, let's just call it straight away, solution dot search matrix. We pass in the matrix and our target is 3. So let's see what happens in this case. So I'll just run this, and you can see we have true printed in the console, which is awesome, right? So I'll copy this and replace it with my old submission on LEETCODE and see how well that would turn out. So my other submission had a very good runtime, but in terms of memory, it wasn't good, because somehow LEETCODE is telling me that I am creating more space in memory, which is true, because current row, right, creates an array each time we iterate. So yeah, that was true. That's fair enough. So I'm just going to take this, right? So I'll just replace this with my current implementation and run this. Hopefully there is no errors, so there are no errors at all. And let's submit this and see what happens. Sorry, let me let me submit it again so that it appears here on the so now you can see. I'm not sure why the solution was supposed to be O of m times n, right? But you can see that did not do well in terms of runtime, but in terms of memory it did well. I think each solution is a trade-off for the other one, right? So this is my last submission. My last submission had a 96.53 percent in terms of runtime, which is 36 milliseconds, right? How many test cases? I don't know. Anyway, this is good. So we did O of n times m. Now let's solve one last question before I leave. So we want to find the intersection of two arrays. Now there are several ways we can do this, right? We can use set and use the intersection to find the intersection of the array. But since we are studying binary search, right, we'll use binary search to do that. Now the intersection of a set between two sets is such that the resulting value has to be a value that is part of both. Let's say, let me remove this. I have a set like this. I'll put a set of numbers 1 2 3 4, and then I have another one 3 5 4, right? Now the intersection between these two sets, right, the intersection will be such that when we group these two sets in on a universal plane, right, this have to have the same value in the middle, right? So let's say we rearrange these sets, right? We are going to have 1 2 3 4 and then 5 here, right? This set here has its 3 4 5 values, right? And then this also has its let me represent this with another color. This is like this, and then this one here is like this. So these are our other set, right? So I mean, the intersection is whatever is in the middle here, right? And we know this is going to be equal to 3 and 4. So how do we do this programmatically? Well, we know how do we do this in terms of code, right? Well, we know there are several helper functions, right? So let's say we implement a set on this array here, right? This set will return all unique values, right? And we will also transform this into a set. Let's just assume that this was an array and this is also an array. Now when we implement the set on this tool, we can then use the intersection function to get the intersection between these two sets, right? And then we will, you know, get the intersection at that point, right? So basically we'll have this set, right? This is going to be a set, and then the intersection will just return, you know, another set for us, which is going to be 3 and 4, and we'll simply transform this into a list, right? This will be, you know, an array with 3 and 4 in it. This is good, right? This works fine, but I'm not sure, you know, we want to use helper functions to help us do stuff. So one way to do this is to use a binary search, right? We already know binary search work on sorted arrays, and when the array is sorted, we can begin to look for a target within that array. So in this case, we can implement a binary search in a way that we sort one of the arrays, right? So we have, you know, 1 2 3 4, right? Although this is already sorted, let's just say we have a sorted array, right? We have a sorted array like this, and then we can use the second array as our, we can use every item in the second array. I'll say R2, this is R1, right? We'll treat this array as our array of the binary search, where, you know, we search for a target within this element, right? So let's say this is 3 3 4 and then 5, right? So this will be, you know, we'll search for each value within this array using the binary search. So we'll treat each item in the second array as a target, right? As a target that we are looking for in the second array. And when we find that value, we will simply insert that value into a set, right? Just to make sure that we don't, you know, include duplicates. So we put it in a set, and then we return that set as a list at the end of the day. So that's how we can use a binary search to solve this problem. And I'll just go ahead and do that now. So let me just copy this here, and this solution, I mean question 349 intersection of two array. So I'll just say here binary search new file, sorry, new file. So this is going to lead dash 349, right? 349, and this is going to be intersection of array, right? Intersection of array, and let's just paste this here. I will import this here, this list. So we have two arrays, right? Two arrays. We are returning an array at the end of the day. So let me implement the brute force solution. I'll just go here, right? I'll call this the brute force solution. So I'll do this, say here new, sorry, refactor, rename. Oh sorry, not this one, cancel. I'll call this brute force solution. So refactor, redeem. This is going to be copy dash brute force. Okay, and then we'll just do this. I'll create another one for an optimized version. So I'll say dash optimized version. Okay, so now the brute version is just going to be, so we'll create a set, right? We'll call this set 1, and I'll set this to a set. Okay, let me show you what sets are quickly. So I'll go to my playground and say, you know, I have an array I have an array of you know, let me see, nums is equal to 1 2 3, and then 3 2 5. Let me just do it this way. Now you can see we have duplicates, we have other values in it. So when I print, when I say, set 1 is going to be equal to set of these nums here, right? When I do this and I print the set 1, right, you'll see we'll no longer have those duplicates in it. Now we have, unique values in this set here. So that's what we are going to do here, right, as our brute force solution. Let me close all of this. So it's going to be our brute force solution. So I'll just put, nums 1, right, 1, and then I'll do the same thing for nums 2. Set of, you're going to be set nums 2 like this, and then what we do instead here, we will just say, okay, now we want to return, I'll just set this to result, right? I could do this with a single line of code, right? But I'm just separating everything for you to see, the steps that was taken to arrive at the solution, right? So I'll say result is simply going to be equal to set, oh sorry, this is set 2 here. So we'll have set 1 dot, so intersection of set 2, and we simply do this. We simply return the result as a list. Otherwise this will just return a set which is in a form of dictionary, but we want a list instead. So this will transform the set into a list. And yeah, so that's all we need to do. I'll just copy this and run it in LEETCODE. Oh, come on. So here, let me just move this across. Oh, crack. So let me just move that there, and I'll just paste this like this. Now, are there any edge cases? So we can have constraints. Constraints, just the nums will be at least have one item in it, okay, which is good. So I is going to be between 0, okay, no problem. So valid integers, right? So let's see when we run this, right? Let's run this and see. Now this worked, right? But I am not sure how well LEETCODE would take this. So let's submit this and see. Hello. Now you can see this worked fine, but you see because we are using sets, right, we are creating extra space in memory. Even with this list here, we are also creating more space in memory. So how do we optimize this, right? How do we optimize this in such a way that we don't go overboard, right? We don't go beyond where we are supposed to be. So I'll paste back the solution here. Okay, let me just copy everything here. I'll bring it to this side and I'll erase everything. Now we want to use a binary search to perform this. First of all, we need a sorted array. So I'll say sorted nums is going to be equal to I don't even need to do it this way. I'll just say nums dot sort, right? Sorry, nums 1 dot sort. So we sort this num here. Now it is sorted, and then here is what we need to do. Now we will be left with a binary search problem, but this time around we are going to do it with O of n time, right? Because we have to search within the second. We have to use each item in the second array as our target, right, to search within this nums1 here. So I'll say at the end of the day we'll need a result. So I'll say I'll still call this again results, or what are we leaving? Okay, I'll say intersection. Nah, that's just not good. So I'll just say results. Results here is going to be equal to a set, right? This is a set here. Now here's what we need to do. We will iterate. Let's implement a helper function. I'll call this a binary search. So I'll just say define bin search, right? Bin search. And for the binary search, we need a target, right? So we'll simply pass in the target anytime we are iterating. So I'll put this here. I'll put the target, and I will not put nums2 because nums2 is already here. I don't want to, copy it over and over again. I'll just use this as my, hold on. I'll just use the sorted nums1 here as the array in which I want to search for the targets, right? So I'll do this, right? And my binary search will either return a value or will return, my binary search should return true or false, right? Because if it's true, then I'll add that particular item in nums2, or in other words, the target to my results here, right? Or whichever value we are looking at. So let's do that. So first of all, I'll need to so we know the binary search is simply a bunch of left and right pointers. So I'll create my left is going to be equal to 0, obviously. Let me do it on the same line. Left and then right. My right pointer is simply the last item in the array we want to search, right? So the last position, so it's going to be the length of the nums1 minus 1, right? So this is going to be the last item, right? We get the mid value, right, or midpoint. So I will just put mid is simply equal to the left plus the right, divided by 2, rounded to the nearest 0 value, right? So here is what we need to do. Here's what we need to do after getting this midpoint, right? We can just go ahead and use this because that's really all we needed to do. So we just say if the value at the midpoint, right? I can just put okay, this will be even better. So I'll say mid value, right? Mid value is simply equal to the nums2. It was nums1 I sorted, right? Nums1 at mid, right? Nums1 at mid. So if the mid value is superior to the target, right? To the target, then here's what we need to do. We simply need to, reduce our right pointer, right? Right pointer is simply going to be equal to the mid minus 1, right? And else if the midpoint is less than the target, right, then we need to raise our left pointer. So left is going to be equal to the midpoint plus 1, and otherwise we simply would do this. We'll just take we'll return true, right? We'll return true. So return true, because I said this function return true or false depending on whether we found the value or not, right? If it returns false, we don't add anything to our result, but when it returns true, we'll add that particular value to our result. So here's what we need to do. We'll say oh Christ, I need a while loop. Sorry. I don't know. I simply forgot about this. I need a while loop to iterate through everything. My bad. So here's what needs to happen. So we'll say while the left, the left is less or equal to the right, right? Left is less or equal to the right. Then we'll do this. I'll just paste this here, right? This will happen. So we find the midpoint each time, right? Get that mid value, right? Which is from nums 1, right? And then we'll compare it to the target. The target is simply going to be a value in nums 2 here. So when we return true or false, so once this is done, we can return false, which means we did not find the value we are looking for. So what do? We just go ahead. Let's iterate for I don't need to use I, so I'll say for nums for num in nums 2, right? I'll just use nums 2 like that, nums 2, right? And then I'll say so for nums in nums 2, right? Let's say if a call to this binary search, right, is true, then we'll add it to our set, our result here. So let's say if bin search of our num here, our num is just simply going to be the target. Our number is simply going to be the target. If this, right, if this is true, then we just say results dot add, right? We don't do append, so we can do add. In fact, we can just we can't do that, because I mean, if we created an array and just append to the array, we might end up with duplicates, right? So let's not do that. We'll just do add, and we'll add the num to it, right? So in the end, here's what we need to return. Once this loop is done running, we just return a list of the results, result here. Oh, come on. So that's all we need to do. Oh, hey, wow, there were some chats in the comments, I mean in the chat session, and I did not. Oh, good. Oh, thank you. Gamacha Gaming. Yes. Thank you very much. Sorry, I mispronounced your name. There's Lama Kane. Is that Cam or Kane? I'm not sure what I'm reading, but I've not with my glasses. Yeah, thank you very much. Thank you. And it is nice to have you guys in the chat. Thanks for coming in. I really appreciate your presence. Okay, so let's move on to this. I'll just let's test this out in LEETCODE, right? So I'll take this here. Okay, that was my previous submission. Let's try a new submission. So I'll run this as my hopefully, fingers crossed. Yeah, so the test cases have been passed. I mean, once you know binary search, I mean, all of these questions come in handy. I did not even need to think much to actually solve this, provided that I've practiced binary search a lot. So yeah. Okay, you can see this was the best solution in terms of space and time, right? It's really good. It's indeed an optimized version of the previous one where we're using sets to calculate the midpoint. So I'm just going to push this to GitHub and round off for this session. Git add git commit -m. I solved 2 questions, so I'll say optimized what was it? intersection of array, not intersection of an array, but I did with okay, optimize 2D matrix, 2D. Okay, I'll just say lit the number of the lit code question, lit 74, 74, and you know, solved lit 349, like this. Okay, so that was it. I'll just push this, so you can have this solution in the description. Git push origin main. Okay, so here is, yeah, that is what I did, and it's almost 12 p.m., which is 12 a.m. So thanks for coming in. I really appreciate everybody that was here, and we'll continue tomorrow. See ya. Bye.